Welcome everyone. I'm Zihong, the Business Development Manager at East 101, and I'll be the moderator for the webinar today. Good afternoon, good morning, or good evening to you, depending on your time zone. As you can see on the screen, if you haven't done so, please make sure you're muting yourself and your cameras are off. And if you are not seeing the instructions, the presentation on the screen, please click on the icon for our presenter today, Anuar Hamid, Dr. Anuar Hamid. And the other instructions I think don't apply in this case. Right. Instructions to make sure your experience is as smooth as possible will be available in the chat. If you need help, please type !mark and help to bring up. And to open the chat box, please look for the icon that looks like a speech bubble in the bar with microphone and video controls. Thank you for attending our event. I'd like to welcome everybody to the second webinar to the East 101 webinar series. I'm sorry, I'm hearing some noises. As I mentioned earlier, if we could mute our mics, and that would be most helpful for everyone. So thank you for attending our event. This is the second webinar under the East 101 webinar series. We're glad to see you here. If you like our content, we hope you will help us by spreading the word. For those of you who might be new to us, we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through process simulation technology. Our founder is engineer Rafael Elias, and we have offices all over the world, but centered in Kuala Lumpur. Our track record includes projects which cover transient or dynamic simulation-based engineering services for design and troubleshooting, flow assurance analysis, operational assistance, especially the operator training simulator solutions or OTS, and process simulation training. A list of our clients here, if you might recognize some of them. Today's webinar is made possible with the help of Schlumberger. They're a one-stop shop for all your oil and gas software needs, from subsurface to topside systems, all with easy-to-use interfaces and a high degree of customizability, which enables your models to behave more realistically. Please contact Tung or visit the website if you would like to learn more. For any inquiries with regards to our services, please contact myself, Lee Zihong, or my colleague Avinash at the numbers and email addresses shown. More information is available on our website, east101.com. Through the East 101 webinar series, we hope to cover a wide range of topics, from upstream process design to downstream and refining, monitoring and surveillance, as well as analytics and AI. The webinar is scheduled to take place every 2 weeks on Wednesdays from 4 to 5 p.m. Malaysia time. We already have our next talk lined up. The topic is molecular piona-based feed characterization and refinery reactor modeling. And the speaker will be engineer Rafael Elias, our very own founder and principal engineer, who has over 30 years experience in the industry. Kindly mark your calendars for Wednesday, the 17th of June at 4 to 5 p.m. That's Rafael there. So before I introduce today's speaker and topic, let's just go over a couple of house rules. We have one speaker this evening who will be speaking for about 1 hour, and that will be followed by a Q&A session. We kindly request everyone to stay muted to avoid any noise and interference. If you have any questions throughout the presentation, please put them in the chat box and it will be addressed by the presenter at the end of the webinar. If at any time someone is experiencing difficulties, please check your internet connection and reconnect to the webinar room using the same link. If you miss anything, don't worry, the recording will be available within a week on East 101's webpage under the Events tab. I see a raised hand in the crowd. Okay, anyway, yeah. So today, our speaker for today is Dr. Anuar Hamid, who is our process engineering manager at East 101, and he'll be speaking on machine learning and oil and gas. Not only is he a simulation specialist with over 10 years experience solving problems at every stage in process engineering, every stage in the oil and gas industry, he's also an experienced data science, analytics, and machine learning practitioner with a PhD in petroleum engineering from the Imperial College London University for work done on computational study in enhanced oil recovery. Without further ado, please welcome Dr. Anuar Hamid to share his knowledge with us.
Thank you, Seham. Welcome, everyone. Good morning, good afternoon, and good evening, wherever you are dialing in from. So today, thank you for your time. Thank you for spending your evening with us at It's 101. So today, what I'm going to do is just to give a bit of flavor and a bit of overview what people are doing or what us in the company doing when dealing with certain problems faced in oil and gas using machine learnings. Uh, so today I will divide my talk into three main topics. One is just to briefly go through some of the examples that what people are doing from various domains. And then that will be followed by some theories and tools for machine learning. And hopefully after that, the last one will be some applications in oil and gas. So the way I see this talk will be based on these three main topics. In terms of attention level, I predict that initially if you look at attention level for say a best student and we baseline that as 100%, I hope that initially for the first part of this talk, people will give their best attention, hopefully because it's interesting. But in the second topic, maybe because of some of the maths of equations that we'll be talking about, there might be some drops in attention. So again, this is just my prediction. And hopefully at the last section of this talk, there will be some spike in interest whenever you see your relevant domain or expertise being discussed. So um, if again, this is my prediction, it's just a hand sketch that I did last night. But if I were to predict the attention level of the students today, I mean the audience today, what I would need to do, I think, is to get some data from the audience. So what I could do is maybe have a camera that will track your eyes, the position of your eyes, where you're looking at one point and where you're looking at next. And then maybe I should also be looking at your body position, your posture. So I could do that if I were to have some kinetic sensor in place. And there are many other things also that I could do in order to monitor the behavior or the attention level given by the audience. So I would call this as input. And then at the end of the day, what I want as my output is the attention level. So remember, what I wanted to do is try to replicate the attention level that the graphs that I showed to you just now as a function of time. So in between what we have between input and output, it's something magical. Is that possible? I don't know. But it turns out people have been doing exactly that. So if you look here, what they did was they have a kinetic sensor by Microsoft, and then they track several variables uh, that that captures the behavior of the students throughout the classes. So if you see the red line in the graphs, those are the attention level marked or defined by a person. So if I were to stand behind the students and I keep track on their attention level, whether they are giving the attention or they are being neutral or they are doing something else or they are sleeping, things like that. So that's red lines. But using machine learning and by keeping track of several variables and several inputs, machine learning will predict the blue lines. So basically what it tells us is that you can somehow give a suitable inputs to your machine learning model. What I refer to model, I'll talk more about model after this. But so for the machine learning, it will take these inputs and it will predict how the student will behave as a function of time in the class. So that is one example of machine learning that people have been using. The other one is by Alex Adam. So again, I'm a bit biased because I used to work with Alex Adam last time. So last time he was doing something um, for computational in reservoir simulation as well, but sort of left academic and went to work in the industry. So this is one of his first work that he did. So he worked for this company called Bosa Game. I think I'm not that sure, but they produced this game called Worlds Adrift. So this game is a RPG game. If you are familiar with RPG role-playing game, is that you will be given a certain map in the game, and then uh, you you are given the chance to explore and then to interact with other players in the game and things like that. So what Alex did was he took a look at several things that the company was tracking. So things like how long the person spend their time, at what time they are logging in into the game, and then if they are in the game, like how many shoots they are taking, uh, and things like that. And then what they could see is that you can somehow map this input, lots of inputs, and then you can map it into four separate or four main categories. So they identified it as socializers. So this is the one that maybe just join the game just mainly for fun and to interact with each other. Some of them is they call it killers. So this group of people, they like to kill people in the game. So they would spend many of their bullets inside the games, for example. And then the other two is achievers and explorers. So this kind of things, it's very useful for this game company because now they have some actionable items that they could do with this data. So for example, if say I can identify that you are a sort of a killer gamer, so that means you when you join the game you prefer to shoot everybody, so the game can identify you and maybe uh, sell you cheaper bullet, for example, in the game, or cheaper armor, things like that to push you to spend more. So it can be quite daunting and scary if you look at things that those kind of companies doing with our data. So they are keeping track of almost everything that you do online, and most of the time they sort of try to make business decision out of it, but as we can see in the case of Cambridge Analytica last time, they are doing something else with the data. So the third example is the one that is quite recent. So this is called social distancing detector. So this one is what they are doing is this is in Oxford mainly because the model or the machine learning algorithm developed at University of Oxford. What you see here is that the camera will track how the position of I'm going to play again the position of the pedestrian and then tell you on the right whether you are following social distancing rule or not. So that's another example. So now I think I would like to start this to give some demos on what else in terms of machine learning that we can see. So what I'm going to do now is to show you some of. So I'm going to show here. Okay. So this is if you remember just now, there's a machine learning that tracks the social distancing. So similarly, this thing, what you see here is machine learning that detects pedestrian, cars, traffic lights, and so on. So this is so you can see the machine learning algorithm will able to track several things. And then this is the ground truth. So the ground truth means if you were to look at this picture and if you were to mark it yourself, the position of the person, the position of the traffic lights and so on, and compare that with computer vision. So here it refers to the machine learning algorithm. What will be the performance of the machine learning? So you can see here one example that you can tell is that, for example, machine learning now it missed one traffic light. You see here this is the ground truth. There's a traffic light here, yellow in yellow, and here from the computer perspective, it's not detecting this as a traffic light. So as you can imagine, this idea of this idealized world where they've been pushing self-driving car is personally I think it's still far-fetched. So we're probably seeing 5 to 10 years before anything that we can driven as self or be called like fully self-driving cars. Because if you play with the model or if you've seen the model, you can see how the behavior of the machine learning performs. So that's one example. The other examples that I want to give you is let me pull out another one. Just bear with me. Wow. Another. So this is again another machine learning algorithms. What we see here is that the machine learning has been trained or has been set to detect faces. So essentially you give the machine learning a lot of portraits of people. And then now what you can do, it can create fake people. I don't know whether that's a correct term, but what you can do now, can see you can adjust how smiley or how whether you look happy or sad. and then you can also adjust whether it looks like a male or like a woman. So if it's So yeah, this is like the male is just 15%, so it looks more like a woman. So I think you've encountered something similar. I think there's several apps that came out for the past years. Mainly, I think there's one called Face App. So they are basically using the same algorithm, to re, uh, try to recreate sort of fake face, given that they've trained their machine learning algorithms on some specific data that previously done. So I think so in terms of the demo for now is that's all. So I think you can see in terms of what people are doing, it, a lot of things are very exciting things happening. But one of the problems is that how can we translate this technology from other domains to oil and gas domains? So for that, we will look in the third topics in this talk. But for now, I'm just going to go through a very quick theories and tools available in machine learning. So hopefully you will be able to follow. If not, my apologies, because I think the audience for this talk is quite diverse. So I will try to cater for everyone. So hopefully, if it sounds too easy, my apologies, and if it sounds too hard, again, my apologies. Um, Before I start with anything, I just want to define what is a model. So a lot of people, they say, okay, I'm modeling this thing. This is a model of something. So what is a model? So I think this Instagram post sort of captures what I would like to convey if someone asks me what does a model means. So if you remember in high school or in pre-uni physics, we were taught something about projectile motion. So if you remember the equation for projectile motion, it depends on uh, the area when you throw something, and then the amount of gravity, and then in the equation also you can see time. So as a function of as the time progresses, the projectile motion will move further away. Uh, so if we use that, so if this is equation that define the projectile motion, so I'm going to call this A model. So I'm going to put that in this box. So now what we have is a model, and given initial velocity, initial angle, gravity, and time, this model will predict what is the horizontal distance, what is the vertical distance. So I want to make that clear. So that is what it means by model. And I think we've seen before in previous slides, uh, there's a lot of stuff. There's a model in between, but at the end of the day, you have something as an input. It may be some data from your plant, some data that we track from people when they are browsing and things like that. And then there will be some outputs that we are interested in. In this case, we are interested in horizontal distance and vertical distance, for example. Um, but in oil and gas, if you look from upstream, midstream to downstream, there are several models or that we are familiar with. So for example, for upstream, so this is where if you're not from oil and gas industry, so this is where the where we found the oil, and we sort of drill around the region to suck all the oil from subsurface up to the ground. So so this is the upstream portion of the oil and gas. And then we have something that is called midstream. So this is typically, at least in Malaysia, this is in offshore. So where you have oil, gas, water coming out from your reservoir, and then you need to send it somewhere. But if you want to send that somewhere, you might need to process it first, or you might need to do something with it. So this is what we call midstream. And if you're not familiar, you're not from oil and gas background, this is where we found the platforms offshore Terengganu, for example, where you have several facilities for midstream. And then the last one is where you have your downstream section of oil and gas. Again, in Malaysia, you would see this in Port Dickson, in Melaka. So this is where you get your crude, and then you feed it, and you want to make sure you get something that you can use out of it. So again, for the upstream model, so we are dealing with, in this specific case, a reservoir model. So reservoir is where the oil, water, and gas are in the subsurface. So when you want to take out those fluids, what you have to do is you have to predict how they will move on the subsurface. So usually what we do is we try to model. So this reservoir is basically rocks, permeable rocks that allows oil, water, and gas to go through these rocks. So usually in this kind of model, you have to define or give inputs, the number of wells that you want. Maybe water, oil, gas, oil contacts. So that defines how much oil that you have, and where the location of the water, because the water is not that useful. And then gas again is not that useful because it's quite cheap compared to oil. So you want to make sure where the location of this contact is. And then you also need to define rock permeability. So permeability is basically like how easy the fluid will flow across this rock or reservoir. And then we also need to know like time, define time. Saying if I were to take out oil today, what will happen in the next 10 years, for example. So these are, again, this is input, and then we have a reservoir simulation model. So, and as the industry standard, we typically use Eclipse and Petrel. So Eclipse is the main engine running this computation, whereas Petrel, if you're purely reservoir simulation engineer, you mainly use Petrel mainly for visualization and running case studies. And there's also a new product by Schlumberger called Intersect. So because Eclipse, as it is a very old language. Just like many other software in the oil and gas industry, they usually started off in the 80s. So the language used in this simulator usually is called Fortran. It's a very old code, and usually there are several limitations when one deals with Fortran code. So I believe Intersect is somehow try to move away from that legacy code and move away to a newer, modern, and sexier code lah. And it's called Intersect. And CMG is a different company based in Canada. And based on this model, the reservoir engineer or the petroleum engineer, they're interested to know mainly on how much oil, gas, and water that you will get out from this reservoir. So, uh, so that's basically it. You might have something else, but that's the gist of it. You just want to know if I have this amount, this many wells, and I drill the wells at several locations, how much oil, gas, water I can produce. I mainly want only oil, but oil will come typically with gas and water, so you have to deal and live with that gas and water as well. So this input will then be fed to the next section of the the production chain, i.e. the midstream. So in this case, remember I mentioned the oil, gas, water coming from the reservoir, coming from the subsurface will be transported to the surface. So usually we use multi-phase pipelines. And then the first thing that we usually want to do is we make sure we separate oil, water, and gas, because what happens is that it's easier to transport these three separately in separate pipeline compared to transporting them together in one pipeline. When you transport them together, we refer that to multi-phase pipelines. Um so this is one of the sort of the important things that engineers, oil and gas engineers, would have to look at or to study. And this is also covered by something called flow assurance. So flow assurance usually refers to uh, how can you guarantee a multi-phase flow in a certain pipeline can flow without any disruption. So to do that, you usually use several software or several tools. The one, again, as the industry standard usually provided by Schlumberger, is called PipeSim and Olga. There are differences between these two, but usually they are used together. And there's another one by Kongsberg that is called LIDA Flow, and this is something similar to Olga. So again, in this software, you define your model, and then you have to define your uh, pipe length, pipe diameter, the shape of your piping, and the fluid properties, and a lot of things in between. So at the end of the day, what do you want to look at is usually one of the important things is pressure drop, but you might also want to look at other things like temperature profiles, wet depositions, and things like that. So again, you have a model, you have input, and you're interested in output. Then you have crude, gas, and water. Where does the crude goes? It goes to downstream processing facilities. And in this specific case, we are looking at crude distillation unit. So what happens, you have this crude coming out fresh from the ground, and you have to do something before you can say put it in your car, or if you want to use it as jet fuel, for example. So in order to do that, you have to do distillation. So I'm pretty sure you're familiar from chemistry classes back then, how we can distillate some of the fluids basically by looking at their boiling points. So again, similar things, you have this model. So this model usually sits on top of process simulators. Those process simulators usually from Schlumberger it's called Symmetry. From AspenTech it's called Aspen Plus and HYSYS. From Honeywell it's called Unisim. So you have this model, and then you have to give some inputs, and you'll be interested to know what will be the output. Again, same structure, you have a model, input, and output. But the problem is, in most cases, these simulation models, what I will refer to physics-based model, because you somehow define this model or build this model based on certain physics that you are interested in. This can, however, be time-consuming because you are trying to solve a lot of equations. So, for example, for the reservoir modeling, you are typically dealing with a 3D model. So, for that 3D model, you have a PDE, partial differential equation, that needs to be solved. And then the amount of computational hours that you need is a lot. We are talking about maybe several nights in order to get something useful out of it. But engineers have been working cleverly. So for example, in their model, they might do some optimization and then something that will try to make sure you can run this computational very fast. But one of the things that people have been looking at is whether there's a way to come up with a simplified model where you have the simplified model to represent the simulator or physics-based model, and then you have this input. I'm not sure what the input will be, but I'm only interested to know what, in this case, pressure drop will be. And I know if my simplified model behaves as it should be, if it gives me the correct pressure drop as per defined or as observed in my physics-based model. So to come up with this simplified model, um, there are many terms or many um, ways, and some of them they are overlap, some of them completely different. But you might have heard people refer this thing as a reduced order modeling or ROM. Sometimes you heard petroleum engineers or reservoir engineers call them surrogate model. If you're talking to, say, a control engineer or a process engineer, they might refer this to transfer function. If you talk to advanced process control engineer, they like this thing called model identification because they want to identify the model and use that in this thing called MPC, model predictive control. So this is different, completely different than what you have in a normal feedback control. This is sort of advanced control that uses some prediction of the system in order for you to achieve a certain control objectives. And one of the things that people have been thrown in is machine learning. So a lot of it coming or borrowed from other domains, but now we are pushing it into oil and gas. And another terms that you might heard is that to represent a physics-based or to represent reality, you are using a digital twin as a solution. So this thing, I'm not going to go through one by one, but some people have been abusing it in terms of claiming some stuff that might not be representative by what they have or what they mean. Some of it is because some of them is there's some overlap, so people get confused a lot. But I'm going to focus mainly on machine learning for today. So again, this is so the types of models that I showed here is usually used by process controls engineers or advanced process controls. They like to characterize things in three ways. One is first principles. So this will be physics based model. So we've seen before for reservoir simulation you use Eclipse. For multi-phase flow, you use something like Olga or LIDAR flow. For HYSYS, you use for downstream or for midstream oil and gas processing, you use things like HYSYS or Aspen Plus. So this is usually what we refer to physics-based because there are some physics being defined in the background. But there are something that takes different approach is that for this model, I don't want to know what's the physics behind it, but I just want to know what will be my output given the input. So this is what we refer to as black box, and if you have something in between, you might call it as a gray box. So I'm going to go through just quickly some overview in terms of machine learning. So you have heard people have been throwing AI, machine learning, deep learning, and use them maybe sometimes in different contexts. But I just want to highlight that deep learning is it's a subset of machine learning, and it's only become popular for the past 10 years. So a lot a lot of findings or a lot of applications only started to take off from 2010s onward. There are several things that contributed to that. I will go on. I will try to explain that after this. But prior to that, we are dealing mainly with machine learning. So back then in the 90s, it's mainly used for spam detection. So you can, again, you have in your spam detection model, what you have is a representation or a box or a model that will look at your email, and then they will try to understand what is the characteristics of a spam email. So for example, the spelling in spam email might not be uh, as good, or the English might not be as good as a normal person would write. So this kind of algorithm will then flag whether the email is a spam or not. So this has been used back in the past 20 or 30 years, and even the whole idea of artificial intelligence started even earlier than that. So if you look quickly at this timeline. So I think one of the earliest reference to artificial intelligence was by Turing. So Turing devised some tests that will tell you whether you are a robot or a human, a computer or a human. If somehow the robot or the computer can fool the test such that you can't differentiate whether it is a computer or a machine, you will pass Turing test. So this whole broad idea of artificial intelligence has started back then from 1950s, and there's several iteration of spikes in interest in AI or machine learnings, but we started to see a lot more interest for the past 8 or 10 years, mainly uh, after this thing called deep learning revolution, where people start to use many useful useful application of deep learning. One of the things, or two of the things that contributed to deep learning revolution is, one is the amount of data available. So if you remember back then, we don't have Facebook, we don't have other social media or other social network. So we had little data to work with back then. But now, since people start to go online, there are many things for people to study and to learn from. So that is one. The other thing that contributed to deep learning revolution is the computational power is just become faster, better and better, especially with the fact that many of this computation usually or traditionally computed on your CPU, on your computer. So CPU is what your Intel is for. Whereas now you can perform the same computation in this thing called GPU, graphic processing unit. This is what NVIDIA, if you're a gamer, if you have a GPU unit in your machine. So nowadays we can perform machine learning computation on GPU, and that speeds up the computational time by several order of magnitude. So now we are here in 2019, 2020. We're uh, we are still learning as an industry in oil and gas, but before we do that, I just want to define some of the common tasks that a machine learning or machine learning algorithms would do. One is the classification. So this is just like your spam detector, whether an email is a spam or not. So that is classification. Regression is something like if you want to predict, for example, if I have this data about a house, the location of the house, the size of the house, whether it's a flat, a condominium, or a bungalow, things like that. I want to predict how much the price will be. So this is regression, is predicting a continuous function. Another thing, so classification and regression, this refer to something called supervised learning. I'm not going to go into that, but just bear in mind there's another sort of another sub item that sits behind machine learning is supervised and unsupervised. And example for unsupervised learning is clustering and dimensionality reduction. Clustering is something that, if you remember from earlier slide, is Alex, one of my ex-colleagues was doing. They were trying to have this high dimensional data, a lot of data. What they want to do is try to cluster it, or try to sort of map it such that you can see it easily. So if you remember last time, this high dimensional data, Alex sort of map it into 4 or 5 type of gamers, if you still remember from earlier in the slides. So this is if you were to learn machine learning today, this is one of the things you will learn. Like if you were to pick up a programming, the first thing you will learn is hello world. But for machine learning, the first thing you would be working with is this thing called Titanic dataset. So Titanic dataset is that a compilation of data that will tell you the age of the passenger, the gender, whether it's a first class or second class and things like that. And then it will tell you whether the person or the passenger survived or not during the Titanic disaster. So the task here is that given the input, remember we have this thing input, and then we want to know what is the output. In this case, survive or not survive, yes or no. And then we have to somehow come up with a model in between. So this model is usually you can represent that as just a linear regression, but that won't work. But you can also use machine learning to come up with this model in here. So again, for regression examples, I've talked about it before. If I have several characteristics or several data or several things that define about a specific house, and I want to know what is the house price, I can come up with a model, a machine learning model that can tell me that. So one of the things that the machine learning or the algorithms that we could use is neural network. I think I've covered that before. So neural network is just so it can be intimidating if you just look at the diagram, but believe me, if you were to look at the math behind it, it's quite easy. If you were to do it manually, it's quite easy. So what you have is basically, if you remember your m equals to mc plus, y equals to mx plus c, your straight line equation. So what you have is m and c as two variables for you in order to define a straight line. So this one is something similar, but you have a lot of m's and a lot of c's in your model, and then you have to sort of come up with optimized m's and optimized c's in order for you to predict or to come up with a machine learning model. I'm sorry if that is not that clear, because I hope that sort of give you some idea how it works. So if you remember, I mentioned something about input, and then you have model, and then you have output. And if you remember, a lot of the tasks previously was mainly looking at pictures or videos. So for this kind of data, your input will be your pixel. Here you'll be the pixels in your pictures or videos, and then you can also perform neural network to do regression or classification. I'm going to skip that. I think we are a bit.
Yes, I was about to tell you. You have 10 minutes left. Thank you.
So again, the neural network. So Yan Lichun is one of the main, the guy that came up with this thing called convolutional neural network, and it's almost in almost all computer vision problems nowadays, using some variation of convolutional neural network, and it's being used a lot in Facebook, in and in all other technology companies nowadays. I'm going to skip this one. So the common tools that we have for machine learning, I'm a bit biased here because I'm sort of an advocate for Python. So there's a lot of tools available in Python. Python is just a programming language that you can use to do machine learning computation very fast. But you have other tools as well, tools like R or MATLAB that can do machine learning studies. But again, I'm showing here only for Python because I'm a bit biased when it comes to the language that we should use. So now, hopefully, I will quickly go through some of the examples in oil and gas. This is one example from Imperial College where they have a model of reservoir. So this is red is where you have fluvial in your reservoir, or ancient river in your reservoir where you have very high permeability in the reservoir. So you can model the flow or the fluid inside the reservoir by using reservoir simulator like Eclipse, for example. So that is shown on the left. Um, but in the research, again, this is a research project. In the middle here, what you can see is some representation of machine learning. Try to learn based on some learning. It will try to predict the behavior or the flow of the oil, gas, and water inside the reservoir. And you can see the machine learning model in the middle here. It can, to a certain level, predicts the behavior from what you would see from a physics-based simulator. Um, Another example is, I'm going to skip this. This is another example I think that people need to be aware of. It's using convolutional neural network. People have been using satellite data to track something. So there's this company called Kairos based in Paris. They buy a lot of data from ESA, European Space Agency, and they try to to do monitoring for oil and gas industry. So for example, on the top left, what you can see is the emission of methane, I think. So based purely on your, mainly on your satellite images, you will try to predict the emission level, the methane level in the atmospheric, in the atmosphere. Again, this is using the convolutional neural network that I mentioned. I just want to highlight that the company Kairos also do a lot of monitoring on the site or on the plant. So if you are coming from operator, just be aware that there are several companies that are using satellite data. They are looking at your plant. So they are monitoring things like the amount of oil that you are keeping in your tank farm, for example, and then they can alert, or they will alert that to the oil trader, for example. If I know there will be a shortage of oil in this region, then I alert to my oil trader to do something, or to make some action out of that data. So some people are doing, even though they are like, you might not aware of that, but some people are using satellite data to monitor your behavior or your productivity. So this is another example. This is our own in-house example, is where we have plant data, uh, lots of plants data, and then we fit into a model, a machine learning model, and then we do something that is called, if you still remember, dimensionality reduction and clustering. So this is sort of try to take a lot of this data, try to somehow project that to a simpler, or to a simpler, easier to visualize data. So one of the things that we observe in this example, you have several clusters of data, and some of them you can flag easily. This is the data that correspond to normal operation. This is the data correspond to plant shutdown, but there are some outliers that you can see here and here. So in that case, you might want to look at that outliers and then try to see what was happening during those periods and whether that contributes to, for example, your plant failure or not. So you can use this thing a lot. Again, if you have lots of data, especially good for oil and gas industry where you have many data that you can process and do something out of it. I think we have another 6 minutes, so I'm going to do the last demo. I just want to share what we have in house. So my apologies if this should be okay. So I just want to show you some regression, multivariate regression using deep learning. So this is basically, if you remember, say for example, if I have a pipeline and if I have a lot of inputs coming in, the pipeline length, diameter, oil, amount of oil, water, and gas, and things like that. And I have some output. So I can use, say, Olga or PipeSim to calculate this. But if I somehow want to come up with a simpler model, what I can use is I can do regression. But regression is, in this case, it's a bit difficult or a bit complex because you are dealing with a lot of input. So you are basically doing with highly non-linear regression. So what I'm just going to show you is that if you are dealing this or if you work on the code on day-to-day basis, these are the things that you will be looking at. Again, this is considered much easier than what we used to deal with back then. This is considered pretty nice code or interface to work on. So I'm just going to try and run this quickly. So what we are going to do now is here we are importing some data into the workspace, and we pre-process some of the data. We review some of the data here. Here we create the neural network, the machine learning or the model to represent the data that we have observed. So now it's running, I think. Yeah, it's running. So the way it works, there's another step in machine learning that is called optimization, where if you remember back then, if you were to have a sort of data that looks quite straight and you want to fit it with a straight line, so what you have to do is you define your straight line and then you start to adjust your M, your gradient, and your intersect, your C. You adjust it manually. So what you're doing is basically you are optimizing your M and your C to find some sort of best fit representation of your data. So what machine learning is doing is something similar. It's just it's a bit more complex, except it's a bit more complex and time consuming compared to normal or a linear regression. So now it's doing some regression. I think I'm going to let it running first. But later what you'll see is that let me check how long this thing will run. I think we're almost finished. Maybe not. But if that's not the case, I'm going to go to another demo first. So I'm just going to show you some of the demos that we have in-house. So you can see here a lot of the machine learning model, someone needs to work with code mainly to come up with something useful. But at its 101, what we've done is we try to put another layer of abstraction on top of this code such that you don't have to deal with the code directly. So that is one of the main ideas or the main reason why we are doing this thing called virtual lab in-house. So it's mainly used for now for internal training. So and apart from machine learning, we also have different application or different things that can be coded into Python easily. And then what you're seeing now is everything is in browser. So everything is using. So for now, it's still using my machine, but I can deploy this thing easily on a cloud. And then if you were to access it from somewhere, you're basically using the cloud to do the computation. So in this case, like internally, what we are doing, we are giving training, and then we will train people, and then let the students try to understand or digest. Say, for example, what is the impact of having, say, a faster tuning for your PID control and things like that. So this is a bit different than what machine learning is, but it's using the same tool. But what I mainly want to show you here is, if you remember what we are doing here is we are dealing with code. But now we can avoid that if we put another layer of abstraction on top of the code. So now what you can do, you can also do regression here, but it will be much easier. Um, so now you can just drag and drop your data. So again, if you have, say, plant data or data that generated from PipeSim or Olga or HiSys or AspenTech or Unisim, and then you somehow want to do some regression, you can't, I can guarantee you that you can't do it easily in Excel. So what you have to do, if you have to have some representation of non-linear behavior, so you use machine learning, and then you can do it easily if you have this kind of interface. And then you can select the structure of your neural network, and then you can provide some of the other um, configuration that I haven't touched or I haven't talked about. But at the end of the day, you can then train and run the model easily, and then you can get the same results from what you've seen before. So the model, so this is basically what we have here in the company. So we are still developing these tools. If you are interested in this tool, let us know. And also, if you have some interesting ideas or interesting things for us to either to collaborate, or there's some synergy that we can get from each other, just again let us know. We can develop this as we go. Uh, Moving back to our regression just now, we've finished our what we call training of the model. So now we can see the prediction of the model down here. So you can see the blue and the magenta line is the data. We call it the real data coming from physics-based simulator or physics-based model. And then the black dotted lines the model predicted by the machine learning, by the deep learning. So you can reconfigure your model, and then you can tweak here and there, and you theoretically you can get a perfect representation of your model here if you want to just do a pure regression, multivariate regression. uh, I think with that, I think I should stop now. I have several slides, but I think I better stop now before uh, But before I finish, I just want to summarize in terms of the current state of machine learning in oil and gas. You have I would characterize these solutions or the offerings out there in terms of three categories. One is standalone machine learning applications. So this is usually a company would approach an oil and gas operator, for example, and come up with a standalone uh, application for something that they are interested in. For example, there are operators that are interested in predictive maintenance, where they want to keep track many data from their plant and somehow predict when is the next failure of a specific equipment. So that is one of the offerings provided out there. And the other offering is integrated with first base simulator. So for example, there are reduced order models in symmetry. So if you are not familiar with symmetry, symmetry started off as VMG sim slash icon. So if you're coming from Petronas, you might be familiar with icon, but there's also sort of twin or a siblings for that simulator that is called VMG sim, that used to be based in Canada, but it's now been transferred to Schlumberger, and Schlumberger now rebranded as Symmetry. And now there's a lot of functionalities being added on top of Symmetry. One of them is this cool things called reduced order modeling for the reactors. And I think, I'm not sure whether, probably Rafael will cover that some of that thing next week, hopefully. And the other things that I've seen is the integration of tools in Python. So for example, the model that I showed you, the machine learning that we were using just now, it was written in this thing called TensorFlow. This is by Google. So if you were to do machine learning today, you don't have to write your own machine learning application, but what you have to do is just use someone else's. So one of the popular ones is called TensorFlow. And what AspenTech is doing is that they are integrating TensorFlow directly into their software called DMC3. DMC3 is being used mainly for APC, for advanced process control. So they are not reinventing the wheel. Instead, they just take TensorFlow and put it on top of DMC3. And so this is sort of idealized version of integration between machine learning and symmetry. And then another layer, what I would call semi-integrated machine learning, where you can somehow link Python or other languages easily to the simulators. One of them is we have this thing called Python toolkit, where you can still build your model or run your studies in PipeSim, but you can do that easily from Python. And if you want to do, say, multivariate regression, you can run your PipeSim from Python and then get back the data and then process the data in Python. So that is what PipeSim is offering. HYSYS and Aspen Plus, there are no sort of native application, but you can also talk from Python to HYSYS or Aspen Plus using COM. COM is the component object model by Microsoft. So basically, if you have different Microsoft application together, you can talk, say, from Excel to Word document. You can also do the same from HYSYS to, from Python to HYSYS and vice versa. And then the third offerings provided by oil and gas companies, independent studies or projects, where you might have a certain things you want to look at, and then you sort of chunk that out and try to see whether the companies out there can deliver some solutions or provide some service using machine learning. With that, I would like to pass back to Zehong. And thank you for your time. I was hoping I would be able to run some of the some of the slides, but I think we should stop now to respect the time that we have. Back to you, Zihong.
Thank you, Dr. Anuar, for a most insightful and entertaining session. Clearly, we can make this another, maybe a follow-up part 2. We might have enough material for that. So look forward to that in the future, maybe. Thank you all attendees for attending. The question and answer Q&A session will begin soon. We will try to keep it to about 15 to 20 minutes. If you feel like leaving at any time, please feel free to do so. And we would like to take this opportunity to remind you that we have our next talk lined up. Dr. Anuar, if you could bring up the slide. Our next talk will be on molecular Piona-based feed characterization and refinery reactor modeling, to be presented by engineer Rafael Elias, our principal engineer, and it will be taking place on 17th of June, which is a Wednesday. Please mark your calendars for that. So that's 2 weeks from now. And yes, the time, as usual, 4 to 5 p.m. Thank you, Wee-un. And yeah, so please, once again, special thanks to Schlumberger for supporting our webinar. For those of you who are interested to learn more about their software solutions, please contact Tang at the number and email listed, or visit their website. With regards to services, you can contact myself, Zihong, or Avinash at the numbers and email address listed, or visit our website at East101, as well to view the recording of this webinar once it is uploaded. We also have a LinkedIn, so if you'd like to follow our LinkedIn page, you can stay up to date with our activities over there. Would anyone like to ask a question to Dr. Anuar?
Okay, I've got one question.
Hi, may I know who's speaking?
This is Hidayah Idrus.
Hi, Hidayah.
Yeah. So I was wondering if the neural learning or deep learning, as you call it, would it apply to reactors with, say, catalyst kinetics? Is it something that can be applied?
Sorry, let me make sure I understand. Dr. Anuar, would you like to respond to that? Or
Yeah. I think
try
I heard the questions. The question was, if I were to have a reactor with catalyst, can I model that using deep learning? So basically, whatever you have or you can think of where you can fit this structure, where you have input, you have somewhere something in between, some box in between, and then you have output, can be translated into machine learning model. So for example, for reactor modeling, if you were to do this using physics-based modeling, you might have to define the reaction, the kinetics of the reaction, and things like that. So you can use all these variables that you think that will be sensitive to the results or important to the result as an input. So, and then you have this deep learning or machine learning in between, and then you have output or something that you are interested in as the output. So you can run that a lot of times in your physics or your first principle models, and then you can start train the machine learning or deep learning, and then you will do regression of those physics-based model, and you can use that as representation of your reactor model. So this is what, for example, symmetry is doing. So So you have you build or you have this physics-based model, but you somehow run a lot of cases, create some if it's uh, some surface or some results, and then try to replicate that using deep learning. When you're happy with the replication or the results given by machine learning, then you can use that model somewhere else to do something like optimization, for example, and things like that. So you are not relying on your model based, your physics based model anymore lah. Once you transfer your calculation to your machine learning. Yeah. I think
Thank you,
that
Dr.
I
Anwar.
hope that answers the question.
Okay, thank you, Dr. Anwar. We have 3 questions pending. The first is from Encik Haziq, who says, Salam Doctor, do you know of any efforts to use machine learning for upstream purposes that are other than reservoir and fluid flow related?
I know there are several teams working closely with Petronas. I know there's one platform they are using that they are doing predictive maintenance where they keep track of many variables on your plant, and then as I mentioned, they try to predict whether your compressor, for example, will fail next week, and if so, what sort of action needs to be taken today to avoid that and prolong that failure of the equipment. So I know there's one platform that using one variation of machine learning solution. The other one also, I think it's being used. I don't know whether it's been realized or not. I believe there's an effort to do um, some monitoring and prediction of wax deposition in pipelines using machine learning, but I'm not sure whether that has been deployed or not in the field. I hope that answers your questions. But yeah, but definitely the other thing that if I remember correctly, there's a lot of interest in using machine learning for drilling, but from what I've seen, it's mainly in research stage as of now. But I'm not sure whether it's been used widely for in the field or not. I hope that answer.
Thank you, Dr.
the
Anwar.
question. Yeah.
So next question coming from Mr. Kumar Kaluri. Can you please give little more details on the integration of TensorFlow with Aspen DMC3, if possible, and similar use of machine learning / artificial intelligence in process optimization space? Thank you.
So for the MC3, it's not out yet. The only reason I know about this because I went to one of their user conferences held online about 2 weeks or 3 weeks ago. So they are releasing it in the next couple of months or so. But what was the second question, Ziong? If you can repeat that.
Similar use of machine learning or AI in process optimization space, I believe.
Yeah, I've seen where people again as similar to the first answer, I've seen people use some sort of simpler representation of physics-based model and replicate that in machine learning and use that machine learning model for your optimization. Because for your optimization, usually what you need to do, you need to run a lot of the same things many times. So one of the things that you're looking at sometimes it's something that is called Monte Carlo simulation, where you might see if you're reservoir engineers. So for Monte Carlo simulations, what you have is that this thing called your physics-based model, where it will take some times to run. But if you want to do some sort of optimization, you will not be running that physics-based model. But what you will do, you create a surrogate model, some representation of that physics-based model using machine learning or other methods, and then you use that simplified model to do your case studies and optimization. So I've seen people doing that lah, to answer your question.
Thank you, Dr. Anuar. We have two more questions to go. First one from Hafiz at MMC. Hello, doctor. What do you think is the number one challenge or barrier preventing the industry from fully embracing machine learning in making business decisions, etc.?
I think at this point, as I mentioned, the main challenge is how we can transfer the knowledge that we've observed in other industry to oil and gas. So there's a lot. I don't know whether you've seen my last slides. There's a lot of resistance in change because we've been doing things and it works most of the time. So if I were to embrace this new thing, whether it will work or not. So that is one. The other thing is that a lot of stuff, machine learning cannot provide you with everything. So one of my last slides would show you that whenever you have machine learning, you would need some domain expertise. So those two categories needs to work together closely to come up with a certain solution they want. So so I see there's still some disconnects between, say, data scientist team, which usually are computer scientists or coming from IT background, and traditional engineers, where you might not be necessarily familiar with machine learning, but you have this domain expertise that might be able to translate or to come up with a good or feasible solution for oil and gas. And I think there's still a disconnect between these two, because if you look at different industry, you don't really need this integration to be that tight. I give you one example. For example, I talked to my friend who works as a data scientist at one telco in Malaysia. So what he does, one of his job was to predict, like if you sign up for a prepaid line using the one of the telcos, they want to predict like whether next month whether you are still a subscriber or not. What happens the months after that and things like that. So that is what we call churn rate. So the how frequent people drop out from their subscription. So so when I talked to him, he was saying, okay, for us it's okay. Like machine learning or data scientists can do anything, because the worst thing can happen is that 1% or 2% will drop the subscription from telco A and will go to telco B. Whereas in oil and gas or in engineering domain in general, you have other things that needs to be considered, because it involves safety and it involves lives, at the end of the day. Yeah, I hope that answer that question. Yeah.
Thank you, Dr. Anuar. That was very interesting perspective. Okay, two more to go. First one from a student, Jason. Hi, Dr. Anuar. I'm Jason, currently a student, still a beginner in machine learning. Would like to know, usually how long does it take you to create a machine learning model? Can machine learning models be created in any IDE?
Yes, in any IDE, depending on what language or what tools you're using. So the main one for machine learning, the main one I would say is there are three main ones. One is called TensorFlow, that is by Google. The other one is called PyTorch by Facebook. So this is mainly for deep learning and it's been used in a lot of applications worldwide. And then the third one is what we call sklearn. So this is doing something mostly other machine learning tasks that is not covered by deep learning or covered by PyTorch or TensorFlow. So for these three tools, they are all in Python. So you can use any IDE as long as you can connect that IDE to Python. To answer the questions, how long does it take? It really depends on like for me, when I started off doing this thing, there are two main challenges. For example, if I were to read the tutorial, uh, or try to follow the tutorial, I couldn't, and given that the fact that when I started this, I was not fluent in Python yet. So when I read the code, I can't tell whether I don't understand the code or I don't understand the algorithm or the math or the uh, um, machine learning part of the code. So I think those are two things that might be the stumbling blocks if you were to start a machine learning journey today. But my advice is to pick up, I think it's one of your slides, is just to stick with a language. The main one is Python and the other one is R, but I hate R. Um, it's mainly used by not physics-based graduates. Anyway, so either Python or R. So if you use Python, you have access to um, PyTorch, TensorFlow, sklearn, and then you can do a lot of stuff. And if you want to come up with a machine learning model, you can come up with in one night. But to come up with a good machine learning model, that is a different story. I think that answer. I hope that answer that question.
Thank you, Dr. Anwar. One more question from Inche Azwan Shaharun. In your view, what is the current state of participation in upstream oil and gas industry when it comes to handling the first hurdle of big data, i.e. data ingestion? As you know, data comes in many forms and formats, and how consumable the state of the data is always a challenge.
Yeah, hi Azwan. Yeah, I think if you follow or if you are friend with a data scientist, they will tell you one thing. They will say people think data scientist is sexy, but the sexy part of the job is probably 10%. Well, the rest is mainly to handle the data, to clean the data, to put the data into a format that is acceptable for the next usage. So I think, again, that also relates to the questions before where there's a lot of stumbling blocks or a lot of resistance in using machine learning's application or solutions. It's mainly the data are quite scattered and somehow we need to translate that data to a more manageable form, such as you put that in SQL database or put that in Excel and so on. So somehow the translation between the dirty data to a clean data, it is not sexy. And it is not many people want to use it. So what we can do is that we can take that chunk of work and we can pass it to somebody who does that in their day-to-day job, because that one requires more experience, or it will take you more time to do that if you don't do it every day. So you might want to start subdivide the task into several smaller tasks, and the cleaning of the data you can be passed to someone who is more keen to work purely on data processing or data cleaning, and then you can put somebody else that say oil and gas engineers that have domain expertise more into the coming up with the correct or the feasible solutions using machine learning. Machine learning. I hope that answers Azwan's questions.
Thank you, Dr. Anwar. Thank you, Hafiz. No further questions for now. Anybody who would like to ask a question, please type it in the chat box. Well, hold on, something came in. Our principal has said something. Can tell people how to get started with Python or Anaconda. Dr. Anwar?
Oh yeah, especially if you're a student or someone who's interested to maybe spend for the next couple of months or years to pick up machine learning. Is my suggestion is to start with this thing called Anaconda. Anaconda is you can see the naming how they give name. Python is the name itself is given from Monty Python, but after that is some variation of reptiles came up when people want to give the name to the company. So another one that is sort of popular is called Anaconda. Anaconda is basically a package manager. So if you remember to do machine learning, you might need different tools. I mentioned about PyTorch, TensorFlow, Scalene, and so on. So this thing might be sometimes confusing or difficult to handle because you have to work with different packages or tools. So Anaconda sort of streamline everything such that everything will taken care of. So you will so by downloading Anaconda, you will get all these bells and whistles that you would need um, if you were to start your machine learning project. But if you're not interested in doing coding, if you think, okay, I'm too old for this, which at one point I thought the same thing, uh, there's this thing called auto ML. So if you can imagine or if you can think about it, if machine learning can learn something, can it learn to auto learn? So it's a bit meta, I know, but it is meta. So basically, instead of coming up the model, you ask another machine learning model to come up with a model for you. So this sort of idea is called auto ML, auto machine learning. Uh, so there are several variations of auto machine learning out there. One of them is by Google. It's called Auto ML. The other one, I can't remember what's the other offerings, but the idea is that you can just drag and drop your data. You don't do any learning. You let the computer to come up with a suitable machine learning for you. So you just have to define what you need, and then it will try to meet your criteria. But then again, sometimes that is not a feasible solution for what you want to do. But if you want to avoid coding, that is one of the things you can look at. Um, yeah, I hope that covers everything, Zeong.
Yeah, thank you, Dr. Anuar. I dropped the link to an article on edureka.co on how to get started with Anaconda for anybody who would like to explore that.
Yeah.
We have a question from Ashvinder. And the question is there any example of computer vision in the upstream sector?
The one that I mentioned was where they use satellite data to monitor your plant. So that is one example. The other example, I know some people start to put camera on their drones. What they are doing with that data, I'm not sure. But there are several claims of using like a robots that can sort of instead of you sending an operator to do say to open a choke valve or to close a well, you can send a robot, and then for that robot there must be some variation of uh, computer vision for that robot to move around the platform. But how feasible or how how realistic that how feasible that solution for a given harsh condition you would observe in offshore, I'm not sure. So yeah, so whatever you can use or whatever you've seen in terms of computer vision being used onshore, you can also apply for offshore. But I don't have other examples that to add on top of that.
Okay, thank you, Dr. Anwar. Once again, thank you everybody who has stayed until the end of the Q&A session. I think if you have further questions that you think of later on and you would like them to be answered, please feel free to drop an email to sales@east101.com and we would be happy to direct your question and provide you with the answer if possible. So I think we'll end the session here. Thank you all and see you next time.
Thank you.